All right, we're going to go ahead and get started. Welcome, everyone, to the final day of the 245th meeting of the American Astronomical Society. Congratulations. If you made it today, you have survived a very busy week. One more day to go. Here we go. So this is the press conference session, Exoplanets from Formation to Disintegration. It is 10:15 a.m. on Thursday, January 16th, and we're in National Harbor, Maryland. My name is Susanna Kohler. I'm the press officer of the AAS, and I am assisted today by Carrie Hensley, the deputy press officer of the AAS, Lexi Galt, who is a graduate student at Indiana University and our AAS Media Fellow. And I will also have assistance from Jill Molesky from Green Bank Observatory for the Q&A session, running the mic around. Thank you. So, just a reminder to silence any cell phones or anything else that might make noise as we start this session. And a note that we are recording this session and we are live streaming it to YouTube. It will be archived there later and added to the press kit. So you will have access to all of the videos of the briefings there, and as well all of the videos from previous sessions. They're all included in the press kit, which is on the AAS 245 meeting website under the press heading. And you can also access it via the Slack channel, press conferences. And that has all been updated with the videos, with the press releases from the presenters, and also with their slide decks. So if you've never been to a AAS press conference before, the way this is going to go is I will give a brief introduction to the session and introduce our presenters. Then they're going to go through and give their presentations back to back, and we ask that you please hold your questions during this time until the end. And then after that, we will go into a joint Q&A session for everyone, and we'll take questions from folks in the room. We've got a handheld mic that we'll take around, and we'll also take questions from anybody who is joining us online. Online, if you are there and would like to ask any questions, you can queue them up at any time via the Q&A box in the Zoom window. We ask that when you do so, you please identify yourself and your affiliation so that we know who you are and who your question is for as well, please. So all that said, we are going to go ahead and get started with our session, Exoplanets from Formation to Disintegration. We've got the whole gamut covered. This is our exoplanet grab bag session for the day. So we're going to go ahead and start out with Taylor Kutra from Lowell Observatory, who's going to present on an ALMA survey of circumstellar disks in young binaries. Next, Ben Hord from NASA Goddard Space Flight Center will present on a new NASA mission to characterize exoplanets and their host stars. Then Scott Wolk from Smithsonian Astrophysical Observatory will present on X-rays in the prime of life, irradiating vulnerable planets. Then Marc from Massachusetts Institute of Technology will present Bright Star Fading World, Dusty Debris of a Dying Planet. And Nick Tusay from Penn State University will discuss how JWST has exposed hot rock entrails from a planet's demise. If you're here for destruction, we're getting to it. All right, so with that, I will set this up. Anybody online want to enable transcripts so that I can turn it off? We're just going to assume that won't pop up. Okay, Taylor, all yours.
All right. Thanks, everyone, for coming. I'm really excited to start off the session by telling you about a survey that I've been doing with the Atacama Large Millimeter Array of circumstellar disks in young binaries. So I think a lot of the time when we think about star and planet formation, we sort of gloss over the fact that it exists within a much larger environment. And for the things I'm going to be talking about today, that environment is the Taurus molecular cloud. It's this huge structure of gas and dust. And there are stars forming all over the place with a range of sizes. But what's unique is that most stars don't actually form isolated like the sun. They form with a friend. Systems of doubly starred systems or multiple starred systems, binaries or tertiaries. And if we want to understand star and planet formation generally, we should understand them in these like more these really common but interesting and challenging systems. So in order to talk about planet formation in these binaries, we first should probably talk about single star planet formation. The general picture looks a little bit like this. You start off with a cloud of gas and it collapses under its own self-gravity. That gas is usually sort of spinning slightly. It's not stationary in the air. And so as the gas collapses, that's how you get your star. And as it pulls all the matter in, it starts to spin faster. The same way that like a figure skater, they pull their arms in, they do those wicked scratch spins, and they spin really fast. But have you ever noticed that when they do that, what happens to their skirt? Sort of flutters out, right? So if the star is the figure skater here, the skirt is what's called the protoplanetary disk. And it's inside that disk that the planets form. And so that's what we're going to be looking at. But in young binary systems where there are multiple stars, there's sort of two flavors to these disks. There are circumstellar disks. So there are disks around either star in the binary, either component. You'll hear me call them the primary or the secondary. And then there can also be a circumbinary disk, a disk encompassing both of the stars. And today I'm going to be talking about mostly the circumstellar disks. And so we looked at those with the Atacama Large Millimeter Array, this huge radio interferometer in Chile. And these are a bunch of my collaborators that have been a huge help during this project. And today I just want to highlight one fun system for you, and that is DF Tau. What you're seeing here is our data from ALMA, and you can see two disks, one in the center around the primary, one off to the side, that's the secondary. The white oval that's overplotted is the orbit of the binary. The stars here are separated by 14 astronomical units. So that would be like putting another star in the solar system between Saturn and Uranus. The disks here are, maximum 3.5 AU. So the entire disk would fit inside the asteroid belt in the solar system. And this system in particular was puzzling because we were not at all expecting that second disk. In fact, for a long time, I tried to kill it because we really didn't think it should be there. And that's because of our pre-ALMA picture of DF Tau. The pre-ALMA picture was sort of based off of something we call the SEDs, the spectral energy distribution. It's a way of thinking about the amount of light emitted by a source as a function of the wavelength. And this is sort of like a little diagram of what they kind of look like for these young stars. They're kind of wonky and have a bunch of features that we can break down that are components that are contributed by multiple sources. So this piece, there's like a maximum, that's just light from the star. So if we see that, we know that there's at least a star. If we see a bunch of emission that is redder than we know the starlight to be, we typically attribute that to disk light emitted from the grains in the circumstellar disk because they're warm. And then towards the blue side of the starlight, we get this other feature that we actually attribute to something called accretion. It's matter from the disk falling onto the star. And so this is how we sort of build up a picture of a young stellar system without being able to directly see where these individual pieces lie. And when we looked at DF Tau, we were able to look at the individual components of it. And this is what the spectral energy distribution looked like. So you have brightness or flux on the y-axis, wavelength on the x-axis. And the primary star is the one in the center, and the secondary star is the circles, the lighter circles. And you'll notice two things. This disk light, this sort of redder light, around the primary there's a bit more, around the secondary, there's less. The gray line is sort of what we expect for just starlight from a star of this type. And so we're like, okay, there's not extra disk light. And also the blue side, the primary is accreting. It has matter falling from the disk onto the star, whereas the secondary isn't. And so that allowed us to put together this picture of DF Tau that looked a little something like this. So we had this orbit, we have a disk around the star, the primary star, the star in the center, with matter actively falling onto it, and then there wasn't something around the secondary. But as you saw before, we found two disks. We found one around both of them. So how do we reconcile this? Actually, the things that I told you about, the things I pointed out in the SED, are more indicative of an inner disk. They point to a disk which is very close to the star, falling onto it or right next to it. And so one way that we can reconcile this is by saying, okay, maybe this secondary star, DF tau b, it doesn't have it has an outer disk, but it lacks an inner disk. There's a hole in the middle. And there's a term for this around single stars. They're much bigger and the holes are much larger, and they're called transition disks. So maybe DF tau b is sort of like a mini version of one of those. It's a scaled down transition disk. And so, like I mentioned before, this is just one of the stars in our survey. These are the rest of them. And we're really looking forward to understanding, star formation, star and planet formation generally, and specifically the interesting scenarios posed by these fun little systems. Thanks so much.
Exciting.
Apparently.
Really open.
Yep.
Perfect. Okay, we're back. Good morning, everybody. My name is Ben Hord. I'm a postdoctoral fellow at NASA's Goddard Space Flight Center, and I'm here today to introduce and share some very exciting news about NASA's upcoming Pandora smallsat mission, which will characterize and observe exoplanet host stars as well as observe exoplanetary atmospheres. So in brief, the Pandora smallsat mission is a space mission. It's host to about a 0.5 meter diameter mirror. It will launch into low Earth orbit, and it will have a 1-year prime mission, during which it will observe at least 20 known exoplanets of all sizes, as well as their host stars, which are low mass main sequence stars. It will observe these planetary systems in both the visible and near infrared wavelengths simultaneously. And as of this month, I am thrilled to announce that Pandora's spacecraft bus has been completed. So here you see an image of the spacecraft bus in a thermal vacuum chamber, and this is a huge milestone towards the completion of the spacecraft and puts Pandora on track for its launch readiness date this fall. The spacecraft bus is a critical component for the Pandora mission because it serves as essentially the brains of the entire observatory. It helps with navigation and orientation, as well as receiving and processing commands from the ground. So this is a big step forward towards Pandora accomplishing its primary objectives of observing exoplanetary atmospheres. So in order to observe these planetary atmospheres, Pandora will use a technique called transmission spectroscopy. And in transmission spectroscopy, we observe a planet as it passes in front of its host star, and we watch as the light from the host star filters through the atmosphere of that planet, and we collect it. And as the light from the host star filters through the atmosphere, the chemicals and the compounds in the atmosphere absorb and scatter the light at different wavelengths. And so that causes more or less light to be blocked when we see the transit. And so by looking at each wavelength and determining how much light has been blocked, we can build a spectrum and begin to back out what chemicals and compounds are present in the atmosphere of this exoplanet. But this assumes that we have a good knowledge of the starlight that's entering the atmosphere as it filters through. And that's not always the case. Like our sun, exoplanet host stars are complicated. They have dark, cool spots and bright, hot spots. And we collect not only just the light from the atmosphere, the filtered through the exoplanetary atmosphere, but we also capture the light from other parts of the star. And so if we don't have a good map of what the stellar surface looks like, we could be totally missing what imprints that the exoplanet atmosphere is making on that light as it filters through. And so this hasn't been too big of an issue so far, but now that we're in the era of the James Webb Space Telescope, we have the precision that this becomes a critical problem. So here you see exoplanet GJ486b. It was observed by James Webb, and you can see that the spectrum looks like there's some wiggles that might be features, but when we actually try and model and see what those features might be, it's extremely difficult to determine if it's a water-rich atmosphere or if it's all due to contamination from the host star. And so this is of critical importance. We want to know if water is in atmospheres of these exoplanets. And the stellar contamination from the spots on the star can mask or mimic features like water, which is not great. So Pandora hopes to address this problem by observing these host stars and their exoplanets in both the visible and near-infrared wavelengths simultaneously. So in the visible, it will track the brightness of the star over time and see those bright and dark spots as the star rotates and how the spots evolve. And so we'll capture it on short and long timescales to see how that changes and get a good map of what the stellar surface looks like. In tandem, we will also be looking at the near-infrared to gather a spectrum of the host star, but also very importantly, we will use our near-infrared spectral capabilities to obtain a transmission spectrum of the planetary atmosphere. So combining our context from the star, we will be able to then account for those stellar effects in our atmospheric spectrum. And it's very important to do this all simultaneously because stars change so frequently. Pandora's observing strategy is unique, and it will enable us to do this. So Pandora will observe at least 20 known exoplanets, 10 times each, and each visit will be a long stare of 24 hours, and these visits will be spread across its year-long prime mission lifetime. And this is very important because the short time scale allows us to get the short-term variability of the host star, whereas the multiple visits across the year give us a bigger picture of how the host star evolves over time. So this will allow us to model the host star spot fraction, measure how these spot changes affect the star spectrum, and in turn, allow us to isolate that exoplanet atmospheric signal. And so this plot shows some simulated data from Pandora, and we expect to robustly detect water and or clouds and hazes on all of these planets that we anticipate observing. And so this is going to be a very powerful method for the entire host of exoplanet missions and observatories going forward. Pandora will lend its unique multi-wavelength simultaneous observation capabilities, as well as long-duration stares at these targets to the greater host of NASA exoplanet missions and observatories. Pandora will also be flying at the same time as the James Webb Space Telescope, and so our hope is that Pandora will help James Webb data be even more precise by providing context and understanding for these host stars in these planetary systems. Pandora will also set the stage for future missions like ESA's Ariel and NASA's Habitable Worlds Observatory. So in summary, Pandora is on track for readiness later this fall with the all-important completion of the spacecraft bus. Pandora will separate stellar contamination from the exoplanet spectrum, and Pandora will measure potential signals of water in these exoplanetary atmospheres if they are present. Thank you.
That one way again.
Be down. She clicks that, yeah.
The same thing, could it relaunch it? There. I got it. All right. So I'm here to talk to you about one of these young stars, Wolf 359. This is a late M star. And to cut to the chase, the star is very, very X-ray bright, and that can be very bad for exoplanets, which we would hope to host habitable life. But there's hope. And let me explain what all that means. So we generally in this community look for life around M stars because of convenience. We know a G star has life, has least one, but it takes about a year for a habitable planet to go around that star. So it would be fairly difficult to study other life-holding planets around G-type stars. So we look at the M stars, they're very, very numerous. A lot of them are very, very close, and the orbital periods are very, very quick. The problem is that the X-ray irradiance of these stars is very similar to the sun. So in the optical, the light gets very, very faint, so habitable planets have to get very close, but the X-rays stay very bright. So the X-ray irradiance these kinds of planets are going to experience is very high. We picked Wolf 359 for a number of reasons. It's very close. It's one of the closest stars to the Earth. It's an M6 star, and that means it's about 11% the mass of the sun. It's about 14% the radius of the sun, and it's only 1/1000th the luminosity of the sun in the optical. And that means that the habitable zone, that's that area where liquid water we think can exist on the planet, is very, very close. It's about 2.5 to 5 million miles away from the surface of that star. When we started this investigation, there were two putative planets, one on either side of the habitable zone. There's still some controversy about whether those planets exist, but we learned earlier in this meeting that most M stars seem to have planets around them, so it behooves us to understand the habitable zone around those planets. And this particular one, Wolf 359, is about 1 billion years old, and will be the future site of the Battle of the Borg, for those of you who follow Star Trek, in about 2.5 centuries. I can't discuss that yet. The transporter hasn't been completed. So we're going to focus on the fact that we did measure this star. It has about 1 solar luminosity of X-rays, which is similar to the prediction. But what that means is that if you were at a similar distance to Earth in terms of the amount of optical luminosity you were receiving, you'd be seeing about 1,000 times the X-ray luminosity of the Earth. And this is a common kind of star. Barnard star is a very similar star. Proxima Centauri, which also has a planet going around somewhere near the habitable zone, is similar. So this is a common problem. And I'm going to cut to the chase of what we observed, which was we were able to measure both the X-ray and the extreme ultraviolet emission from the star and calculate what that meant in terms of mass loss on the planet. And what that meant was that if you were at the distance of the Earth, you're seeing about 1,000 times the X-ray luminosity that the Earth sees, and about 1,000 times the amount of mass is exiting that planet right now, if it has an atmosphere, as is exiting the atmosphere of the Earth. But even if you were at the outer edge of the habitable zone, you're still losing about 300 times the mass of atmosphere that the Earth does. So how bad is that? Should that worry people living on a planet there? And the answer is, well, if you have 1 Earth atmosphere, it could survive that attack for about 2 million years. These stars stay active for about 4 billion years. So that is not a good balance for an atmosphere surviving. And some of that was mentioned earlier in this meeting. However, if you have a Venus-type atmosphere that's actually about 100 times more massive, and you could have that atmosphere survives 200 million years, that's still not long relative to the 4 billion year activity, and things are looking down. But if you were to strip away the atmosphere from the Earth today, yes, it would be a bad day for us, but the atmosphere would, or the ocean would evaporate and actually fill in that missing atmosphere fairly directly. So you have to count the ocean mass as a replacement atmosphere. It's a reservoir for new atmospheric material. In the case of the Earth, that atmosphere could be refilled for about 600 million years. Now, the Earth has an ocean depth of about 2 miles. So if instead it had an ocean depth of about 15 miles, then the atmosphere could be replaced as long as we needed to. So there's some hope, but there are also some problems. This star is active, so if we put what we observed into a movie, you'll actually see it flashes and pops a few times in the amount of time we looked at it. We only observed the star for 4 hours, and these traces show the luminosity as a function of time going across. And so these 2 little bursts we saw were 9 times the solar luminosity in X-rays and 8 times the solar luminosity in X-rays, and that ups the budget of X-rays that this planet saw to 10,000 times what the Earth saw. So then we went scrambling into the archive and tried to figure out how bad the situation was. And turns out XMM had observed this star for about 60 hours. And overall, we count 18 flares over about 3 days. This biggest flare is about 100 times the solar luminosity in X-rays. So that's a really bad day. That's about 100,000 times what the Earth sees. But it's all about statistics. It's all about what the overall experience is. And so we took this 3 days worth of data, did a little extrapolation. How would this look over 1 million years? Okay. Big extrapolation. So there are some errors here, but the long and the short of it is, when you look at all these flares, they're not the driver. It's that quiescent flux that really is the driver. This is a little bump on top of that. And so what that means is you have to add a little bit more ocean. So 8 oceans wouldn't be enough. I hasten to say maybe 11 oceans. Oceans 11 would be plenty. It does work out that you will evaporate 10 oceans worth of material, leaving about 1 left over. And so if you are lucky, yes, an exoplanet like this could support life. It's a corner case, but remember what I said in the beginning. There are lots of M stars. So there are lots of exoplanets. And so these are the cases we can be looking for. And I'm just going to end with a little visualization of what this looks like when you have one of these active stars. It's flaring a lot. You can expect that exoplanet going by is losing material. You saw a little bit of it drifting away there. These flares are going off. They're interacting with the planet. A lot of them might be missing, but this goes on for millions and millions of years, and it just becomes a race condition. So thank you. Do this without killing it. You kill it. Oh. All right. I'm getting good at this. You quit it, you bring it back, you go to our session.
Thanks.
And it's all done. You killed it. Want to try it again?
No, it's on the screen.
Mhm.
It's on the screen, yeah?
Yeah.
Perfect.
Okay.
All right. Hello, everyone. My name is Marc. I work at the Test Science Office at MIT, and we are excited to announce our discovery of a dying, disintegrating world. As a reminder, what we do with TESS is searching for worlds across our galaxy. It's monitoring the entire sky for planets that cross our line of sight, causing these periodic dimming events, which we call transits. Now, over the years, we have identified dozens of small rocky worlds that orbit their host stars way too closely. This is roughly 1 to 2% of the distance between the Earth and the Sun. So these planets, these small rocky worlds, are being roasted. Their surfaces comprise oceans of lava with atmospheres of rocky vapor, evaporated rock vapor. So if there was a hell in space, this is it. Okay. Now, curiously, if these rocky planets are sufficiently large, say the size of Earth or say Venus, then they might be able to hold on to their atmospheres more robustly. But if they were small enough, like the size of Mercury or the Moon, then the hold over their atmospheres become much more tenuous. And this atmosphere, the gases in the atmosphere can expand out into space, where it will cool down and form these dust grains. And these dust grains will eventually coalesce to form dust clouds that form comet-like dust hails. Now, what's in the dust hails are minerals from the evaporated layer of the planet itself. And so this illustration gives you the classic idea of what we might expect a disintegrating planet to look like as it transits the host star. You don't actually see the transit of the planet. It's too small, but you have this large dust hail which obscures light from the star itself. And so this is exactly what we've discovered with TESS. We found such a signal around a bright star, introducing the transits of BD 054868AB. It's a mouthful, But this is a bright K-dwarf, so it's a 10th magnitude K-dwarf, roughly 140 light years away. And in the test data, we have observed periodic dimming events. The period is 30.5 hours, and we can see there are these periodic transits of roughly 1% in depth. This means that roughly 1% or more of the starlight is blocked by some object. And in this case, it turns out to be something resembling a comet-like tail, because the transit profile, the shape of this dimming event, is unlike any other that we've ever seen on a typical planet, which tends to be a box-like shape. Here you see a highly asymmetric profile with a very gradual fall off, or a very gradual, what we call egress, so a return to maximum light that is very characteristic of a comet-like tail that is transiting the host star. Now, when we try to fit the data, when we try to fit this brightness or dimming profile, curiously, we found the presence of not one, but two tails. So there seems to be a trailing tail, which is your typical comet-like tail, and then there's also this leading tail. Well, in other words, it's actually a dust head, but we call it a leading tail because it's in front of the planet. What you see right now is a particle simulation showing what you should expect to see when this planet actually transits the host star. So there's a leading tail, a component of dust that's in front of the planet, and then there's the trailing tail, which is the typical comet-like tail as before. Now, seen from the top-down view, this is what you should expect to see. You have this shorter leading tail on the top right, and then this gigantic trailing tail in the bottom left that extends all the way up to half the circumference of the entire orbit. And this length is 9 million kilometers long. You can wrap the Earth's equator 225 times with such a long dust ribbon. So it's an incredibly gargantuan dust ribbon we're seeing here. Now, if you take this ribbon and if you unroll it, you would expect to see this profile, as shown again by our simulations, where you have this wall of dust, that's the trailing tail, and this stubby little stubby leading tail that blocks off much less light. And the reason why we get two tails here is because we have a distribution, a range of grain sizes in the dust. You have larger dust grains populating the leading tail and the smaller dust grains in the trailing tail. Now, the larger dust grains are roughly 10 microns in size. That's roughly the size of, say, desert sand, while 1 micron sizes for the smaller dust grains are roughly the size of, say, soot particles. Now, because we know the size of this dust tail and we know its extent, we can estimate roughly the volume of dust in these tails, and therefore how much mass is being lost by the planet, how much material is being lost by the planet into dust. And when we crunch the numbers, it turns out it's roughly 1 moon's worth of material every million years. And if we assume that this planet is really as small as Mercury or the moon, then this mass loss, this rate of losing material is catastrophic. The planet will completely evaporate or disintegrate within the next 1 or 2 million years. Now, this seems like a very long time, but in the lifetime of a star or a planet, it's no time at all. If you are to scale cosmic time to the average lifespan of a human, that's like saying you'll be gone by the end of this week. You know, on Sunday, you'll be gone. So we are really, really lucky to be witnessing the final hours of this dying planet itself. You know, it's catastrophic for the planet, but we astronomers are watching here in glee, you know? And the reason for that is because, remember, what's in the dust are minerals from the evaporated layer of the planet itself. And one of the big questions that we've always asked is, what are the composition of rocky planets outside our solar system? And so if now we do transmission spectroscopy, which has been previously described, thank you, on the dust, we can figure out what is the mineral content of a rocky planet. What are the interiors of these rocky planets made out of? And of course, we can use a tool or an observatory as powerful as JWST to target the dust tail and to perform mineralogy of this rocky planet itself. And because we have such a bright target, which has a very obvious transit, we can expect that the data that James Webb could potentially bring on this target would be exquisite. So I'd like to end my talk here by just saying how extreme this system is. We have an incredibly bright target with very large dust tails, and it's the mass loss, that it's showing, it's truly catastrophic. And we're really hoping that the exoplanet geologists out there would have a complete field day with this new dying planet. Thank you.
Okay, I think it's working. Good morning. This is surreal and cool. All right, let's get into it. I would like to thank Marc for going before me, giving you all a primer on disintegrating exoplanets, saving me some time. His test discovery is an exciting addition to a very short list of these objects, and we hope the TAC agrees that it should be a priority target for future JWST observations. Planets have layers, like an onion, if you agree with Shrek. And rocky planets tend to like to keep their insides on the inside. So these systems offer a unique opportunity for us to study their internal layers as they spew them out into space. But not all planets are created equal, and we want to know how special each ball of rock is, including our own. The planet I am here to talk to you about, K222b, is unique in a number of ways. And the slide I'm showing you here is all previous work. But most importantly, it's the only disintegrating planet that has been observed with JWST so far. So let's get into the results. If it'll advance. There we go. In April of 2024, we used MIRI LRS on JWST to observe 4 predicted transit windows of K222b, with 2 of those being in a full phase curve. Here are the white light curves from each of those observations. The full data is grayed out in the background and binned up into the teal points in the foreground. The red line is a very simplistic transit model fit to the data. We had anticipated more activity than we observed, but recent optical observations from a separate study shows that there is an unexpected long-term quiescent trend with an as yet unknown mechanism. Insert your favorite speculation involving magnets here. We did still get a significant transit event during the 4th predicted transit window, and from that we produced the first mid-infrared spectrum of a transiting dust cloud from a disintegrating exoplanet. The unbinned data, grayed out in the background, has been binned up in the foreground with a constant spectral resolution of 17 and in a pretty rainbow color pattern. We also managed to get simultaneous coverage with KEOPS, and the photometry from that gives us a single optical data point as well, albeit with large uncertainties due to its sensitivity limits. At the very least, it suggests extreme optical depth during this transit is unlikely. Naturally, we want to know the constituent compounds that create the spectrum. Assuming this disintegrating exoplanet model is accurate, the compounds in the dust cloud could tell us something about the planet's interior composition. Going into this project, we had a suite of solid dust particle models we were testing for from the literature, with most of the interesting features expected at the longer wavelengths. Unfortunately, that is of course where the highest degree of uncertainty is in our MIRI data, but we can still draw some interesting conclusions. First, we think these data are not consistent with an iron-dominated flat spectrum from a bare core. If you imagine this planet like a ribeye left to bake in an oven too long, after a while you might expect only the central bone to remain. But in this case, we see significant spectral features, so there's likely still some meat left on the bone, so to speak. Mantle mineralogy is a bit more difficult to disentangle because, as I said earlier, most of the interesting differences happen north of about 8 microns, where our uncertainties get rather large. Shown here is just a small subset of mineral models showing how subtle these differences can be. But the keen-eyed among you may have noticed that I have not yet said anything about the most prominent feature, which also doesn't line up with any of the models we were anticipating. At about 5 microns, we see a sharp feature going from significant transparency to opacity, and none of our solid mineralogy models can account for this. So what is it? This was our embarrassing forehead-slapping moment when we realized that we had initially forgotten to consider gas. Given the disintegrating rock model, we have assumed the most likely explanation would be some kind of rock vapor. The most plausible of which is MgO, magnesium oxide, and SiO, silicon oxide. This, according to the literature, intuitively makes sense with the vaporized convected mantle material, which we expect to be some kind of combination of iron, magnesium, silicon, and oxygen. But the models for these gases don't seem to fit the data. So we expanded our search to look for other plausible gas species, and in so doing, we included typical ice vapor models. To make a long story short, we think these short wavelength features are consistent with CO2, carbon dioxide, and NO, nitric oxide, as shown here. What does this mean? How could this disintegrating planet be an ice ball? Well, I usually joke that answering that question is not my problem, while pointedly catching the eye of a pure theorist and preferring not to speculate. But this is a very tantalizing result. And while I think it's too early to make any definitive claims or conclusions, I will say this. Taking these results at face value, this planet must have formed very far from its star and migrated into its present location through gravitational interactions. This is a binary star system, so perhaps they are hurling snowballs at each other. In summary, we have produced the first mid-infrared spectrum of a disintegrating exoplanet around a main sequence star using JWST. The spectrum is inconsistent with a bare core of iron. We are likely seeing a combination of dust and gas with the unexpected short wavelength features indicative of NO and CO2 ice vapor. QR code will take you to our paper, now posted on the archive, and we have also submitted it to AppJ Letters, so keep an eye out for the official published version in the future. In the meantime, please go see all of these plots again in the archive paper surrounded by a bunch of text. Thank you for your attention.
Thank you so much, all of you. All right, we will now go into our Q&A session. So we have a mic here. Thank you. Ethan.
Surprise. Hi, this is Ethan Siegel from Start to the Bang. And my first question is going to be for Taylor. Taylor, thank you for your talk. And I'm a little bit curious for DF Tau, unlike you showed a number of single component systems that you observed with ALMA also. And unlike these other single component systems, there appears to be very faint extended emission coming from beyond the extent of the clearly identifiable disks. Is that potentially evidence for a circumbinary component to this system? And have you looked into the spectral energy distribution of that outer component that doesn't match with the two disks alone?
Great question. Thank you. So some of the systems that I showed on the very last slide were singly disked. There's a disk around the primary star, and then there was like a little star on the orbit. I can show you again later if you'd like. And we don't detect a circumstellar disk around the secondary. I think some of our observations, the disks are just dimmer. They're smaller disks, and so they're emitting less light. And so the signal to noise was much lower. And so what you were seeing maybe as sort of background emission was actually just like noise from ALMA. But you've actually come to a very fun part of this that is confusing to me, is that you're right. None of our systems which have these circumstellar disks also host circumbinary disks. Circumbinary disks are pretty rare. We have one system in our survey that I didn't share that is a circumbinary disk. And yes, placing constraints on A, the prevalence of the circumbinary disks, and B, the amount of material in the circumbinary region is very important, and we'll be doing that in our next paper. Yeah, thank you.
Ed Deviney, Villanova University. I have a question for Ben. That project certainly important, key project, even small project. I was thinking, Ben, there's been a lot of past history of trying to figure out what star spots look like on individual stars. I think of the works of Voigt over the past decades. And would you profit from a campaign to look at the objects that you're interested in like that?
Absolutely. We would definitely benefit from a campaign from other observatories looking at these stars. In fact, the Pandora mission team currently has a working group within it to obtain space and ground-based observations in preparation for launch later this year. To do exactly that, to try and constrain some of the stellar parameters and get back out some of the stellar variability history as far back as we can go to make sure that Pandora's science is maximized and we really make a splash. So absolutely.
Thank you.
Hi, my name is Julia Falcone from Georgia State University. This is a question for Marc. First of all, super, super cool talk. I'm wondering whether you have any ideas about how the planet got into that position in the first place. I'm assuming it formed further out and then moved in towards the star. And if that's the case, do you see evidence of other planets to have a large gravitational effect? Or do you have any other ideas for how it wound up in this situation?
That's a fantastic question. Well, as Nick mentioned, at least for K222b, or the host star to K222b, has a binary companion that might be hurling snowballs at one another, his words. It's the same with this discovery of BD, I just call it BD, the test discovery. We have identified that it has a companion about roughly a few hundred AU away, and we are not certain at this point whether there could have been some form of an interaction between the two of them that might have led to this rocky planet, which may have been farther out, to be hurled inwards much closer to its current host star where it is disintegrating. So that might be one idea.
Thank you.
Back to Ethan.
Hi, thank you. Again, this is Ethan from Starts with a Bang. This next question is for Scott. Scott, you spoke about the planets that could potentially be in the habitable zone around Wolf 359 as though they would be born with a finite amount of atmosphere or surface components that would then be just sublimated away or boiled away over time. And I wanted to ask, could these habitable zone planets around Wolf 359 potentially exhibit a continual outgassing of material from the planet's interior, perhaps even aided by tidal forces from the parent star that would allow an atmosphere to persist or replenish itself even over 4 billion year timescales?
Okay, so it's a little bit more complicated than the way I put it. You start with a lot of atmosphere from the material you're forming out of, so that gives you some protection in the beginning. But the way we understand the atmospheric formation process is through volcanism. And so the volcanism generally runs out after the first, for an Earth mass planet, which we have a couple of examples of, that volcanism seems to run out after about 200 or 300 million years. So that's what you get. Now, I understand you're talking about tidal pumping. These systems should not be capable of that sort of effect you see at Io. It's too far away for that. So you'll get what you get to start with, unless something's imported in from outside in the system, as we've been talking about here. But we don't know what that starting point's going to be. For a system like Venus, it seems to have been very dry. Earth is a little bit wetter. Out on the ice belt, we know there are entire planets that are made of water. So if you get some injection like that, you could be in very good shape. But what we don't think can happen is sort of continual creation of atmosphere. And that's what creates this race condition. You create a certain amount of atmosphere, and then you've got to hold on tight and hope it's enough.
Hi, Mitch Rovalsky from Space Telescope, and I had a question for Ben. So even for the non-expert, it sounds like this mission is not only a significant advancement, but truly transformative in some areas. And so I was curious, in your personal opinion, what is kind of the most interesting question or parameter space that you're interested in exploring that's just not possible without these new observations when they come in?
That's an excellent question. I think it is tough to find one thing that's the most interesting, but I do think that this mission will be revolutionary for M-dwarf science. Getting that visible and near-infrared simultaneous information will be transformative for understanding the surfaces and the stellar physics of M-dwarfs. And as we've seen in this session and throughout the conference, M-dwarfs are one of our best chances at this current time to detect Earth-sized planets, potentially Earth-like planets. And they're intrinsically linked to their host stars. So I think Pandora is going to make some great strides in understanding just what M-dwarfs are like and what their surfaces are like, and perhaps even their nearby environments that perhaps we didn't know before.
Let's move to a couple questions online before we go back to Ethan. Can you bring the mic to Carrie, please? Thank you.
All right, this first question comes from Camille Carlisle at Sky and Telescope magazine for Taylor. What causes a transition disk to form instead of a quote regular disk?
Yes, I was hoping someone was going to ask this because this is where the fun for me starts. I'm trained as a theorist. And so when I see things that kind of don't make sense, I get very excited. So transition disks generally, the fraction of disks which are transitional increases with the age of a star forming region. So they're thought of as sort of like a later evolution of the disk. Some of them have planets inside, like Jupiter-like planets, a bunch of Neptune-like planets, but generally they're older. But the weird thing is that when you form a binary system, doesn't matter how you form the binary, cloud collapse, disk, there's a bunch of different options. But in every single one of them, the two stars form at about the same time. So there's no reason that either of the stars in DF Tau should really be older or younger. And so there's no reason that the disks should be more or less evolved, but they appear to be. And they're also, they're made of the same material. They have the same chemistry. It has the same external environment. So the fun question, I think, going forward, specifically for DF Tau is, when we've controlled for all of these other factors, what triggers disk dissipation? Why is it different? And that we definitely don't know for DF Tau. Thank you.
I have a question here for Scott. This one is from Bill Waller at the Galactic Inquirer. What is the case for nearby M-type stars that are not X-ray bright or flaring?
Well, so the way we think of the situation, the data support that stars form active, and they're active for a certain amount of time. And when it gets to those M stars, that amount of time seems to be in the couple of billion year range. And then there's a transition to inactivity that comes somewhere around 3 to 4 billion years, and then they're fairly calm. So what we think is going on is that most stars or planets are going to form around stars that are fairly active and have this roller coaster of fireworks, mixing metaphors, to deal with for a certain amount of time. And they'll have to get over that. And then the stars seem to shut down fairly quickly. And then you can have a very long, calm time to develop life and very complex organisms. It's getting through that first few billion years that seems to be the issue.
Let's do one more.
Yeah, sure. This one is from Camille Carlisle at Sky and Telescope, and this is for both Nick and Marc. Following up on a previous question, do your results imply that binary star systems should often host disintegrating planets? And if so, are there any constraints on when that would or wouldn't be true, the types of planets and orbits, etc.?
Well, considering that we've only found 3 of these in Kepler and K2 pipeline, and now 1 in test, I would say that it's not fairly common. So still, I would say a small number of statistics at this point to suggest how frequent these things occur, particularly binary systems. I would generally steer away from binary systems, make these common, and more, phrase it as
Sorry, can you pull the mic closer to you?
Sure,
They
yeah,
can't
sorry,
hear.
yeah.
Yeah, no problem.
I would typically not look at it as, binary systems should have these kinds of things, and more like these kinds of things can be explained by interactions from binaries.
Anything you want to add?
Yeah, just to add, I think this could be a very intriguing system for a lot of astronomers or theoretical astronomers who do or study the dynamics of these particular systems, because here is potentially some good evidence that something has rolled in from probably some distance away.
But let's take
The
one more
last
from online, yeah.
Okay, this question is from David Chandler, freelance. This one's for Ben. Would the Pandora observations be complementary to the X-ray observations Scott Wolk described? And thus, could it be a way to confirm the hypothesis of water in these vulnerable planets?
Yeah, that's a good question. I definitely think that Scott's work is complementary to what Pandora is attempting to do. We have a preliminary list of targets that Pandora is going to observe, and we've targeted somewhat active stars because we want to be able to see that there is potential for stellar contamination in the atmosphere and be able to disentangle that. I think that that means a lot of them don't have X-ray observations because they're not super active stars, such as Wolf 359. Again, Scott can correct me if I'm wrong, but that means I think that a lot of these stars don't have any X-ray observations, and so that part of the spectrum of these stars is not very well understood. And so these stars could do well to have that part of the spectral parameter space understood and place constraints on potentially what types of chemical species could exist in the atmosphere. I'm not quite sure all these atmospheres would evaporate away as dramatically, perhaps, as Wolf 359. But the universe is full of surprises, and you don't know till you look. So I think that X-ray is absolutely a parameter space that is worth exploring, complementary to Pandora.
Good, Ethan.
Thank you. This next question is for Nick. Nick, I would like to ask you, one of the things I often see in astrophysics is, okay, we went to look for this thing and we thought to look for like what's the naive thing we're going to look for. Okay, evaporating atmosphere, crust, mantle, core. And then you go and see and you say, okay, well, it looks closest to the mantle, but we don't have everything. There's something in there we can't explain. So then you go a layer deeper and you say, what else could we add to this to make it work? And you said, okay, rock vapor doesn't work, ice vapor does work. And then you publish.
Yeah, that's what happened.
So then I say, okay, but then you stopped. So what else could it be? What else could these spectral features mean other than the first solution that you found that doesn't conflict with the data?
It's a good question. So we stopped because it's the present time.
Can you bring the mic a little closer?
There's still a lot more that we can do, and there's a lot more that I'd love to do, but my time is limited, and I'm trying to do too many things. But no, there's lots more that we can do, and we definitely want to do a more careful analysis. But we also wanted to get this result out there. It's pretty exciting what we do have so far. So there is more that we can do, but I don't want to speculate on exactly, what those results will entail. But I mean, as an observer, I think the best that we can do is get more data. So I don't know. We'll see, but it's a good question.
We've got another, well, okay, go ahead.
Martin Radcliffe with Evans and Sutherland Planetarians for Marc. So you've talked in units of losing a moon's mass every million years. Recently we've heard lots of different units from bananas to camels. Do you have an idea based on that egress light curve of how much mass is in that part of the tail in terms of either, a comet mass? We just had comet 2024 G3 pass through the SOHO frame, although it didn't occult the sun. But based on that, or a Hale-Bopp size, or is there any estimate of the mass of what's in that really dense, opaque part of the dust?
So if I understand correctly, you're asking if I've used units of comets to weigh the trailing tail as opposed to.
Yeah, more, I mean, you've got a certain amount of opacity right in that tail. Do you have a mass measurement of how much has to be there to create that kind of dimming in the star?
So based on the particle simulations that we've ran, it's definitely possible just to isolate that part of the tail and just say, okay, based on what we can measure from the simulations, which is fitted to what we see from the test data, and using some assumptions about the grain composition as well as its density, what is the mass that you can get. So it's possible, but we haven't done that specifically for the tail. But it's definitely an intriguing question because that is indeed the densest part. That's the most light blocking part of the tail as well. But definitely something to look forward to doing at this point. Thanks for the suggestion.
Let's take this last question over here and then we will close out the session. Sorry to cut things off.
Hi, Mitch Travolsky, Space Telescope. Just one bit to follow up with Nick. If you acknowledging the difficulty of observing these systems even when something as large as Webb, what would be, the next logical follow-up as more of these systems are discovered? Would you want UV observations? Would you want longer wavelengths? Or do you truly just need deeper observations at the current wavelengths?
So that's a great question. Thanks, Mitch. So, because these are disintegrating exoplanets and we expect them to be very, the clouds to be very dusty, we're not actually seeing the planet itself, at least not in K222b. We're just seeing the dusty effluents and the gas. A lot of the really interesting spectral features happen in the mid-infrared wavelength range. And so that's why we targeted JWST and MIRI specifically. And so it would be cool to see what else other wavelength ranges could give us, but I'm not sure that we have the flux to do that, to be quite honest. So, if you want to give me time on everything, I'll point everything at you. But yeah, I think more time on JWST is probably the way to go.
All right, we're going to have to go ahead and cut the discussion short. Sorry, but we are over time. So let's give our speakers one more round of applause. Thank you. And thank you again to your PIOs for helping you prepare releases and everything. And thanks to all of you for being here. We hope you will come back and join us. Our next session is sooner than normal at 12:45 p.m. We are going to be running a seminar for science writers on the Vera-Rubin observatories. So we hope you'll come back for that. And otherwise, next press conference is 2:15 p.m. Thanks. See you all.